Hello and welcome to ECE 3030. So in this video lecture, we will be continuing our discussion on CMOS inverters. So this lecture will particularly focus on delay. So we will be following chapter 3, section 3.4 of the textbook by Professor Marilyn Wolf. So with that, let's get started with the discussion about what delay means in an inverter. So now again, so here is the inverter, and what delay means is that if there is an input, for example, change in the input, for example, it goes from 0 to 1 over here. From a logic level perspective, the output will change from a 1 to 0, but this transition will happen after a delay, after a time delay. And similarly, when the input goes from 1 to 0, the output will go from 0 to 1, but again this transition in output will be time lagged from the transition in the input. Now physically, what does it mean? Now here again we are showing the circuit diagram of an inverter where Vi is the input and the Vo is the output. And so here the input is changing from 0 to VDD, 0 volts to VDD. 0 volt stands for logic level 0, and the voltage VDD stands for logic level 1. And if there is a transition like this in the input voltage Vi, the output voltage will go from VDD to 0 volts, and it will have the transition of the output voltage will have a shape like this. And see, the transition in the output voltage doesn't happen instantaneously, rather it happens gradually, and this, the fact that it does not change but instantaneously, rather it takes some time to change, this is what causes the delay. And similarly, when the input goes from VDD to 0, here the output goes from 0 to VDD, but again the change is not instantaneous, rather it takes some time to for the output waveform to go to VDD. And again this, the fact that it takes some time for the output to go from 0 to VDD is what causes delay in an inverter. All right, so now let's see why it happens. So usually in any logic blocks, these are any logic blocks, the gates are cascaded. What it means is that the output of a logic gate is input to one or more gates, other gates. So in other words, the output of a logic gate feeds to the input of many other logic gates. So for example, here we are showing an inverter chain where a bunch of inverters are cascaded, and you can clearly see that the output of this logic gate is the input of this logic, the second logic gate. So this is 1 and this is 2. So the output of logic gate 1 is the input of logic gate 2. So circuit wise it will look like this, and essentially what is happening is that this output voltage, when this output voltage changes from 0 to 1 or 1 to 0, it is basically charging up the input capacitances of this N MOSFET and P MOSFET, or discharging the input capacitances of the N MOSFET and the P MOSFET. So what we can say is that, all right, so this output voltage here VO1 is essentially connected to a capacitor C, where this capacitor C is the sum of the input gate capacitances of the N MOSFET and P MOSFET, and we can say that C, so let's call it CL, and L stands for load. So the load capacitance of the inverter 1 here is the gate capacitance of the P MOSFET. So this is the P MOSFET, and its gate capacitance is CGP, and CL equals CGP plus CGN, and CGN is the input gate capacitance of the N MOSFET. Okay, so what is CGP? What is the equation for CGP? So CGP is simply the epsilon naught, which is the vacuum permittivity, multiplied by the oxide dielectric constant over the oxide thickness, and then multiplied with the area of the gate, which is WP multiplied with LP. And similarly, for the N-type MOSFET, the input gate capacitance is epsilon naught epsilon aux over T aux multiplied with Wn Ln. Now note that both of these MOSFETs have the same oxide thickness T aux, but their width and the gate length can be different, for which we have used two different subscripts for W and L, while T aux is the same for both of them. Alright, so now with this capacitance, it's easy to understand why there is a delay. So the reason is very simple. So say the input changes from VDD to 0. So the input is here, initially it is VDD, but then at say time t equals to 0, it goes from VDD to 0. Okay, so what will happen? So we have seen that when the input goes from VDD to 0, so our input is basically 0. The N-type MOSFET is off, while the P-type MOSFET can be represented by a resistance, which is RTP. And what is happening is that now this is the pull up transistor, so it's connected to VDD. So essentially you get a series combination of the resistor RTP and a capacitor CL. And what will happen is that this capacitor was initially uncharged, and through this RTP it will be charged, and this is the output voltage. So initially the V output is 0, and then as soon as the input goes to 0 volts, this resistance this becomes an open circuit, and as a result this capacitor will get charged up to VDD. And so what we want to do is find an estimate of how long it takes up for this capacitor CL to get charged to VDD. And you can clearly see that this is an RC circuit, and from very elementary circuits theory, what you know is that in this case the output VO is simply VDD multiplied with 1 minus e power t over RTP CL. Alright, so this is the simple RC circuit, so you can easily derive this equation, where it comes from. Now this is so when the input goes from VD2 to 0 or logic level 1 to 0, the output goes from 0 to VDD or from logic level 0 to 1, and this is what we call the rise of the output waveform. So there is a typo here, so it should have been rise time. And so we usually, for delay metric, we use two different metrics. So one is rise delay, which is essentially the time it takes for the output to go from 0 to say the 50% of the final output. So this time is what we call the rise delay, and this is denoted by TDR. And just using this equation, you can say that TDR is 0.69 RTP multiplied with CL. We also use another metric called transition time or rise transition time, and this is the time it takes for the output to go from 10% of its final value to 90% of the final value, and this is just simply equal to 2.2 RTP CL. Alright, so we have seen the rise of the output when the input goes from logic level 1 to 0. Now let's look at the fall time, and this is what happens when the input goes from logic level 0 to logic level 1, or from 0 voltage to VDD. And when this happens, the output goes from VDD to 0, or logic level 1 to 0. Alright, and essentially what happens is that the input has just at time 0, our input has gone from 0 to VDD, and as a result the N MOSFET is an open circuit, the P MOSFET is an open circuit, and the N MOSFET is represented by resistance RTN right now, and as a result this capacitor was charged up to VDD at time t equals to 0, and now this will discharge through this resistance RTN, and this is the output voltage V0, this voltage here. And again, based on elementary circuits theory, you can show that in this case V output will be VDD multiplied with e power minus T over RTN CL. So just like the delay matrix for the output rise, we define two metrics for the output fall. So first is the delay, and this is defined as the time it takes for the output to go from 100% to 50%, and this is called the TDF, the time delay for fall, and this is simply equal to 0.69 RTN CL. And another metric is called transition time, which is the time it takes for the output to go from 90% to 10%, and this is denoted by TFF. So the first F stands for transition and second F stands for fall. So I don't know why we refer to transition with F, but this is how the book refers to it, and this TFF is equal to 2.2 RTN CL. Alright, so the delay matrix for the rise depends on the effective resistance of the p-type MOSFET, and the delay matrix for fall depends on the effective resistance of the n-type MOSFET. So now the question is, how do we calculate this RTP and RTN? Now note that this RTP and RTN is a simplification. Why is that? Because if you look at the transistor ID/VDS characteristics, for example for an N MOSFET, the ID is a nonlinear function of VDS, and as a result it does not have, so the way we are representing it, the RTP as a linear resistor, the MOSFET as a linear resistor, is not formally correct, but this is a simplification that helps us to analyze inverters or even any logic gates very easily and intuitively. So let's do an exercise of how we can calculate these effective resistances based on the ID/VDS curves. Alright, so let's think about, so let's take an n-type MOSFET, and the ID/VDS curve is plotted here, and so the ID/VDS is plotted here for a VGS equals to VDD. Alright, so here is the VDD here, and so the VDD is, this is the ID/VDS curve for VDD, and here is the VDD. And so let's say this is this is the saturation voltage here. So here, and we call this saturation voltage as VB, and this VB, and this saturation voltage is essentially equal to VGS minus VT, and here this curve is for VGS equals to VDD, so it's VDD minus VT. Now to the right, so let's say this point is what we call point, say P, and to the right of it is the saturation region, and to the left of it is linear region. All right, so let us first try to calculate the average resistance in the linear region. And by average resistance, what we mean is that, let's say this is VB, so we take a voltage that is VB over 2. So this is VB equals to 2. So this point is somewhere here, and so we call this point 1, point 1. So this point is called 1, and say the current here is I1. All right, so our V1 is equal to VB over 2. Now what is the I? So now what we know from the square law model is that the current in the linear region is, say, beta multiplied with VGS minus VT multiplied with VDS minus half of VDS square, and here the beta is simply W over L mu C ox. All right, so here what is VGS minus VT? So we have said that VB equals to VGS minus VT, so this is equal to VB. And what is VDS at point 1? The VDS at point 1 is of VB over 2, and then VDS at point 1 is VB over 2, so this VDS square becomes VB square over 4, and as a result what we finally get is 3 over 8 VB square, and this is what we have seen. All right, so then what we say is that in this linear region the average resistance is simply V1 over I1. Okay. And then we can, based on this, we can calculate what the linear region is, so we'll work on that more. All right, so now let's look at the saturation region. So again, my annotations are gone all, so let's say this is the point P as we have shown in the previous slide. So this is VDD, and this is the saturation voltage. So here we have VB, which is VDD minus VT as we have shown in the previous slide. Okay, so now to the right of point P is saturation region, and to the left is linear. All right, so let's take a point here. Let's say this is the point 2, and at point 2 the value of VDS is equals to V2 is equal to just the it is simply equal to half of VB plus VDD, right? Because this point, at this point VDS is VB or VDD minus VT, and at this point VDS is equal to VDD. All right, so the average is simply the sum of this, half of the sum of these two. All right, so now again it's in the saturation region, so the average current here. So the current at point 2 is simply ID sat, and ID sat is beta over 2 VGS minus VT, and what we have said is that VGS minus VT, so VGS is VDD minus VT squared, so this is simply equal to beta VB squared, and as a result in the average resistance in the saturation region is simply V2 over I2. Okay, so then summarizing everything here, so V1 R1 is V1 over, so the linear so this is the linear region, simply V1 over I1, and this is equal to, this comes out to be this, and R2 which is the resistance in the saturation region, and let's say this is V2 over I2, and this will come out to be like this. And then finally the effective resistance RT, we say that is simply the sum of the effective resistance in the linear region and the resistance of the transistor in the saturation region over 2, and then if you just take these two and average it, you will get something like this. Okay, so we have the same equations written over here. So RT is the effective resistance, and this RT, the way we defined it, it was a general form of the effective resistance for both N MOSFET and P MOSFET. So here what we have written is the same expression for N-type MOSFET and P-type MOSFET. Now for the N-type MOSFET, the VT is replaced by VTN, and here the beta here, so beta is simply mu n COX W over L, and here the VB is VDD minus VTN. Now note that VTN is a positive number, so you can actually just get rid of this magnitude sign over here. Now on the other hand, for P MOSFET, the threshold voltage is negative, so the way we write it is just take the absolute value of the threshold voltage of the P-type MOSFET, and again the beta P is mu P COX W over L for the P-type MOSFET, and here VB is VDD minus the absolute value of the threshold voltage of the P-type MOSFET. Alright. Now again the same equations are written over here. Now the two delay metrics that we have written is for rise delay and rise transition time, and fall delay and fall transition time. Now note that for the rise time we have the pull-up MOSFET, the capacitor gets charged through the pull-up MOSFET, which is the P-type MOSFET, and as a result we have RTP here, and also for the rise transition time in the expression we have RTP here. On the other hand, for fall time, when the output goes from 1 to 0, the capacitor gets discharged to the pull down transistor, which is the N-type MOSFET, and as a result we have RTN over here in these two expressions. So again, for rise times, rise delay or rise transition times, RTP goes into the equation, and for fall delay or fall transition time, RTN goes into the equation. Now what happens is that you would want the rise times, the rise delay equal to the fall delay, or the rise transition time to be equal to fall transition time, and as a result you would want RTN equal to RTP. So let me erase that. So again, you would want RTN equal to RTP. And note that in both cases, for the N MOSFET and P MOSFET, the VTN and VTP, you can make sure that the absolute value of the threshold voltage of the P-type MOSFET is equal to that of the N-type MOSFET. You can also ensure that COX for both the MOSFETs are equal. So the way we have written here, we already assume that the capacitance, input capacitance of both N-type and P-type MOSFET are equal. But what is important to note here, mu N and mu P, the mobility of electrons and mobility holes are very different. In other words, mu P and mu N are not usually equal. So usually mu N is larger than mu P. So as a result, what usually happens is that to make RTN, the effective resistance of the N-type MOSFET, to make it equal to that of the effective resistance of the P-type MOSFET, what we usually do is we make sure that beta N equals beta P. And the way we make sure of that is by choosing, so if beta N is has to be equal to beta P, what needs to be done is mu N WN over WLN equal to WP over multiplied with WP over WN LP, and what to make sure that this equality holds, what we usually do is, so let me write it down like this, WP over LP, the ratio of WP over LP to the ratio of WN over LN, we usually make this ratio equal to mu N over mu P. So what does it mean? So again, what we have done is the WP over LP for W over L for the P-type MOSFET is usually much larger than that of the W over L for the N MOSFET, and usually the ratio of W over L for the PMOS over that of the NMOS is equal to the ratio of the electron mobility to the hole mobility, and that essentially makes sure that the effective resistances for the N-type MOSFET and the P-type MOSFET are equal. All right. So next thing is that let's look at how the effective resistance and in turn the delay depends on the various device parameters and also the voltages. Now here I'm writing everything in terms of that of the N MOSFET, but the same thing holds for the P-type MOSFET. So just for the sake of it, let's look at the dependence of effective resistance on various parameters for the NMOS, and you can easily convert all these dependencies for that of the PMOS. Alright, so first thing, if Wn goes up, your beta N goes up, and as a result your RTN goes down. It simply comes from this equation, and if RTN goes down, your delay will go down. At the same time, if your Ln goes up, your beta N goes down, and as a result your effective resistance will go up. All right. So, and also another important thing is what happens if you change the Wn, if your W over L ratio. So if your W over L ratio goes up, your beta N goes up, and as a result your RTN will go down. Okay. Now the threshold voltage VTN, and this is one of the important things, and we'll talk about it again later, but from this equation what you can clearly see is that VTN is both in the numerator as well as the denominator. Now the denominator has a square on it, so as a result it will mostly depend on the denominator. So again, if you increase the threshold voltage, your numerator increases. On the other hand, your denominator decreases, and as a result, if your threshold voltage increases, your RTN will also decrease, will also increase actually. All right. Okay, so now VDD. So again, VDD appears both on the numerator and the denominator. Now note that there is a square. For example, the numerator increases linearly, but the denominator increases quadratically, and as a result, if your VDD increases, your RTN will actually decrease, and as a result, your delay times will increase. Delay time will decrease. And finally, mu n, you can clearly see if mu n increases, your beta n increases, and as a result, your RTN will decrease, and as a result, your delay times will also decrease.